think
you ready?
This is everybody, so we'll go ahead and get started.
All right, good. So let me do a quick introduction. We've got Roby's PhD proposal. I think everybody, it is good to see that we have lots of people here. We do have a couple of extra seats up in the front. It's sort of like, you know, if you show up to lecture late, you got to sit up in the front. But Roby did his undergraduate here at Georgia Tech and then decided to stick around for his PhD. So it's he worked with me as an undergraduate. I think he also did some work for Dr. Lee as well. Finished his master's back in December. Is that right?
February.
February. So it's just time flies when you're having fun. So we're here for his proposal presentation. I wanted to thank Professors Raziknak and Saldana Talenka. We've got Dr. Munir Hilu from NIST. So we all know he's our visiting guy and so forth, you know, on there and so forth. Wanted to thank everybody for serving on the committee and so forth. I think we have some very exciting stuff. Just to preface it, because I want to make sure the bar is held very high, right? We did go over some of this with Mazak. You saw the smooth controller there, and Mazak's CEO made the following statement. He said, well, clearly you know more about our controller than we do. So, you know, not to set your expectations high here, but that's exactly where we're at. Oh, and my apologies, our triangular friend here is Tommy Tucker, so Dr. Tucker, who will be also on the committee. So I think that's it. What I'd like to do is I'd like to go ahead, we'll get things going, we'll hold all the questions until the end, unless there are questions of clarification. Roby's going to go for how long?
50 minutes.
50 minutes. 50?
15. He said 15.
15.
15?
No, 50 minutes.
I was getting very excited.
I was giving you a hint here.
I thought I was going to go early today. So he's going to go for about 50 minutes. We'll have some Q&A from the general audience, then we'll go to the committee. As long as the committee is okay with this, we'll leave the committee questioning open. I mean, people don't have to head off. I think a number of you are gearing up for your proposal as well, so you can see what it's all about. But I do understand that people do have to get off to other meetings and things like that. So you know, you should feel free to head on off, especially after the initial round of questioning.
So is this horizontal tear in the screen or designed in the slide?
Well, that was supposed to be designed. That was actually left over from the old template, and now that I look at it here, it looks exceedingly dumb. So maybe I should have removed that.
It's sort of interesting.
Yes.
It is interesting. I have had colleagues who have done the following. Not the markers that are drawing up on the screen. We will avoid doing that today.
Yeah, maybe it should have gone around.
Yeah, I was thinking about the curve.
That makes
would have been
more
very
sense.
cool, and it would have been a spline, and
Right,
I know
exactly.
exactly what you're thinking, Professor Raziknak. Anyways, Roby,
Okay,
please
so
go ahead.
there are donuts in the back for everyone. Please eat them, because otherwise I will be forced to. So if you could eat the donuts, that would be great. And thank you everyone for coming. Thank you to the committee members and all of the audience members, and welcome this afternoon to my PhD proposal presentation entitled Direct Servo Control of Positional Derivatives for 5-Axis CNC Machine Tools Using Densely Sampled Toolpaths. As you know, my name is Roby Lynn. And so first, I'm just going to go over a brief outline of the talk today. So we'll talk first about CNC machine tools, specifically 5-axis CNC machine tools. Then we'll talk about computer-aided manufacturing, voxelized computer-aided manufacturing, and toolpath generation from voxel models. Then we'll talk about the current programming practices of CNC machines. The primary point here is G-code. We'll also talk about machine tool control system architectures, trajectory planning, and limitations and deficiencies of current approaches. And then we will go to the proposal solution here, which is direct servo control from Voxel Based CAM. And in that section, we will talk about material removal rate analysis and control, some research questions, and tasks and timeline. So CNC stands for computer numerical control. These are machine tools or cutting machines that are controlled by a computer. You can see some examples here on the right. These CNC machines is effectively a servo-controlled version of a manual machine tool, so we can have mills and lathes that are, their axes are controlled by servo motors instead of by hand wheels. And so we can do complex coordinated motion with these machines to cut a variety of materials with high precision. There are a number of different types of machines. On the right here we have a 4+1 axis mill turn machine. This is based on a lathe, and it has a milling head that can index. And then on the bottom we have a 5-axis milling machine. Both of these are on Georgia Tech's campus, actually at our new manufacturing facility. But these aren't the only kind of CNC machines. There are 2-axis lathes, 3-axis machining centers. But for the purposes of today, we'll be talking about 5-axis machines specifically. So 5-axis means obviously you have 5 axes, and each of these axes can control one aspect of motion of the cutting tool. So we can control the position of the tool, the translational position of the cutting tool, and the orientation of the cutting tool as shown in this figure here. So at each point, P1, P2, P3, P4, we have different X, Y, Z, or different translational positions of the cutting tool. And we also have different orientations of the tool that are denoted here by theta and phi. So theta and phi are 2 angles that we can control. So that's 3 translational axes and 2 rotational axes. 5-axis machines allow us to do 2 important things. The first is called 3+2 machining. This is where we machine 3-axis features on planes that are not aligned with the translational servo axes of the machine, such as in this bottom image here. So you can see we've machined planes by rotating the table holding the workpiece, which in this case is the aluminum cylinder, and we've machined planes at different angles here. The more important thing we can do with 5-axis machines is actually complex sculptured surfaces like you see on this King Kong bust, which I have brought today and I will pass around. So we can actually move all 5 axes of the machine at the same time in order to create complex surfaces like this. While that sounds great in theory, the issue is that this is exceedingly difficult to do, and it requires a lot of experience and know-how in order to both program and operate a 5-axis machine tool to do simultaneous, what we call simultaneous 5-axis machining, which is why we use computer-aided manufacturing, or CAM software. So CAM software is the software that links the design process to the manufacturing process in some way. It allows us to plan what are called tool paths for machining a part within the computer from a CAD model. For those who are unaware, CAD is computer-aided design, so we'll design a part in CAD, import that into the CAM software, and then plan the machining process in the CAM software. This provides some level of cognitive offloading from the user because the software is doing the computation to create the tool path. The user is not doing that manually. It allows for visualization and simulation as shown in the bottom here. So again, here's our friend King Kong. The cutting tool is shown in blue here. Obviously the model is in gray, and then here is the tool path shown on the face of the model, and the cutting tool, we can animate that driving along the tool path. So this is really essential for creating 5-axis tool paths because of the number of variables that are involved. We have to control 5 axes in a coordinated fashion throughout the tool path. So without CAM software, this would be very, very difficult to do. So CAM software has been around for a long time. It is primarily based on parametric geometry that's imported from CAD. So this would be boundary representation or constructive solid geometry or some combination of those to define the part model. So that means that the surfaces and features that define the part are described in an analytical way, similar to vector graphics. So they're described by equations, and we can scale them up and down without losing any fidelity. However, for the purposes of this work, actually we are relying on what we call Voxel Based CAM. So instead of using surfaces that are described by equations, we are actually describing surfaces by these small blue squares shown in this image. And this is good for a number of reasons. In CAM,
You mean blue or magenta?
the
magenta
blue squares are the surface, and the magenta is kind of the parametric equivalent. So this allows for simplified collision checking. When we're doing machining simulation, we can have high complexity surfaces that are made up of these little voxels. We can simulate material removal and also deposition if we were doing additive, but in this case only subtractive. We can simulate material removal easily. And the voxel model is actually effectively a large array. So the voxels are three-dimensional pixels. They are cubes. They are not squares. So if we extend an image, kind of the idea of pixels in an image, we will come up with voxels, which are these little cubes here. And so the voxel model is effectively a large three-dimensional array. And in order to speed up processing on the array, we can use a parallel processing platform or graphics processing unit. And so this bullet here, GPU, means general purpose computation on a graphics processing unit, which is what we do in order to accelerate operations on the model. So the side length of the voxel here will be denoted for the rest of the presentation by S. And that determines the resolution of the part surface, similar to how the pixel size determines the resolution of an image. Okay, now, in order to plan toolpaths from a voxel model, there are two important concepts that we need to discuss. We have 5 axes we need to control, 3 translational axes and 2 rotational axes. So the first thing we're going to do is we're going to determine the translational axis positions along a toolpath. And we do this by combining a series of volumetric offsets. So volumetric offsetting is the 3-dimensional equivalent of image dilation, which an example of which is shown in this image here. So dilation means we're dilating the beginning contour, which is a black triangle, by some kernel or structuring element. In this particular case, the structuring element is a circle, as shown by the dashed line defining the circle here. If we drag the structuring element along the starting contour and then record the points, record the points